by Professor Upasana Kashyap, which is from Citadel. Her topic is Picard group of dual operator algebras.
Thanks, Mike, for inviting me here. So this talk is joint work with David Fletcher, and this is very preliminary. It's a very preliminary stage. So I'll start with some background stuff. So first of all, operator algebra. So by operator algebra, we mean a subalgebra of bonded operators on Hilbert space, B of H, which is closed in the norm topology. So we will assume that it's closed in the norm topology. So for any Hilbert space H, we know that B of H is star isomorphic to the space of matrices. So in matrices are basically operators. But more generally, we can look at a matrix of operator. So a matrix whose entries are also operator is also an operator. So mathematically, we phrase the above principle as, so if you look at n cross n matrices whose entries are operator, that is also isomorphic to operator on n copies of Hilbert space. So n cross n matrices over bounded operators on Hilbert space is isomorphic to a bounded operator on n copies of Hilbert space. So a matrix of operator is again an operator. Now, the matrix of operator and bounded operators on a Hilbert space, both of them are a star algebra. Star algebra means they have a, for example, that has a conjugate transpose as a star, and bounded operators on the Hilbert space has adjoint. Every operator has a corresponding adjoint. So those two spaces, they are isomorphic as a star algebra. So their star isomorphism is also preserved. So what is this star isomorphism? So if you look at n cross n matrices whose entries are operators on a Hilbert space, and this is the bounded operator on n copies of Hilbert space, and this is the isomorphism that we define. So we start with a matrix A whose entries are operator in this space. So A is a matrix whose entries are operator, and we got, corresponding to this matrix, we got an operator L of A, left multiplication by this matrix A, where we define the operator L of A, left multiplication by a vector in n copies of Hilbert space, just a matrix multiplication, A times X. So A is a matrix of operator, and X is a vector, a long vector in n copies of Hilbert space. So this is just a matrix multiplication, left multiplication. So by this identification, you can check that the conjugate transpose is preserved, and in fact this is a star isomorphism. So we can identify these two spaces, n copies of n cross n matrices on operators and bounded operators on n copies of Hilbert space. So these two spaces are star isomorphic. So we will turn to the main area of interest, operator spaces. So operator spaces are generalized as a non-commutative norm space. So so we define the operator space to be just a closed linear subspace of bounded operators on a Hilbert space. And V of H is just a space of matrices, and we can thought of operator spaces also as a vector space whose elements are matrices. Every operator space is a norm space because B of H has a norm, so it inherits the same norm as a subspace. So every operator space is a norm space, it has a norm, but it has something more than just a norm. Operator space has a hidden structure besides it's just a norm structure. Besides its vector space or norm structure, it has some hidden structure, which is, again, just recall we saw the matrix of operator is again an operator. So if X is an operator space, then n cross n matrices whose entries are X can also be regarded as an operator. So another way to see this as following. So we define X operator space to be just a subspace of bounded operators on the Hilbert space. So n cross n matrices whose entries are coming from X will also be a subspace of n cross n matrices whose entries are operator. But from the last identification, we identify Mn of B of H as bounded operators on n copies of Hilbert space. So we can view Mn inside a operator, bounded operators on n copies of Hilbert space. So this also has a operator norm. So for every operator space X, it just besides X, Mn of X also has a norm. So the matrix norms are very important in the non-commutative world, because when we solve the non-commutative problems, the norm, we just don't look at the norm on X, we also look at the norm on n copies of Mn of X. So the main point is, if X is an operator space, then Mnx n cross n matrices over entries of X also has a norm for every n. So this is called the operator space norm structure. Because we no longer just have one norm to deal with, but also the matrix norm, so we have the following definition. So if X and Y are operator spaces and T is a linear map, we define T to be completely bounded if this is true. So the completely bounded norm, so if the supremum of the matrices of T of Xij, the supremum over all n and all the matrices inside the ball of Mn of X, this supremum is finite, then we say that T is completely bounded and that supremum is the norm of that map, which is called the completely bounded norm. So in the norm space case, how do you So in the norm space case, if you have just a Barnard space or just even a norm space, we define the norm of linear operator to be supremum of just T applied to all the entries X, where X is in the ball of X. But in case of operator spaces, we replace X by in the ball of matrices of X. And we have, and we take supremum over all such n's. So that's my completely bounded norm. And similarly, you can define completely isometry. Complete isometry, so if we have operator spaces and a linear map between them, then T is called complete isometry if at every stage n, for every level n, the norm is preserved. So you look at the matrix norm for 1 by 1, 2 by 2, 3 by 3. If it is preserved at every level, then it is called complete isometry. So we think of two operator spaces as the same if there is a completely isometric map between them, which is also 1 to 1 and 1 to. So we think of two operator spaces X and Y as being the same if they are completely isometrically isomorphic, which means that there exists a linear complete isometry map from X onto Y. And we write X is completely isometrically isomorphic to Y. Means X and Y, they are the same object as an operator spaces. So their matrix, on the matrix level, their norms are preserved. There is a linear map through which the norms are preserved on the matrix level, and this map is 1 to 1 and 1 to. So these are very abstract ideas, but in 1988, Ruan gave a characterization of these abstract objects purely in terms of norm. So this is called the Ruan's theorem, which says that if you have a vector space with a bunch of matrix norm on it, then that vector space is the operator space if and only if it satisfies these two conditions, which is very easy to check. So this is like a concrete, you can check, if I give you a matrix norm, you can check whether this is the operator space norm, means is it coming from operator space structure. So if you can check these two conditions, then the matrix norm turns out to be an operator space norm. So this was a very convenient criteria to check if something is an operator space, or if you have to prove something is an operator space. So conditions R1 and R2 are called the Ruan's axiom, and Ruan's theorem says that R1 and R2 actually characterizes operator space. So this result is fundamental to the subject in many ways. For example, it is frequently used to check that certain construction which you can make up with operator space remains operator space. For example, direct sum, or if you are quotienting operator space by a subspace, is it a still operator space? All you have to do is check these two conditions. If it satisfies these two conditions, then it will be an operator space. which says that if you have an operator space means you have a linear subspace of B of H with matrix norm, and if you have a product, multiplication on that space, then that space will be an operator algebra if and only if it satisfies this condition. That if you multiply two matrices, the norm will be multiplicated. It means the norm of A times B is less than equal to norm of A times B. And this you have to check for all the level, like A and B are matrices in M and N cross N matrices whose entries are A. So this is the operator space characterization of operator algebra. So many problems in the operator algebra are studied in this setting of operator spaces where we have a matrix norm. So, so the next thing we will look at is the dual operator algebra. So dual operator algebra can be viewed as a non-self-adjoint analog of one-Newman algebra. So one-Newman algebra is star, weak star, closed star subalgebra of B of H. Here we drop the self-adjoint case. So dual operator algebra is just the weak star closed subalgebra of B of H. Being a dual space, it has a weak star topology. So this is just a weak star. This is just a subspace of B of H, but it is closed down in the weak star topology. So there is a very famous theorem given to Sakai in the literature of C-star algebra, which says that one-Newman algebra is the same as C-star algebra, which has a Banach space pre-dual. So in the setting of operator spaces, there is a non-self-adjoint analog of Sakai's theorem due to Lamerdi, Gletscher, and Modena, which says that dual operator algebras are exactly the operator algebra which has a operator space pre-dual. So instead of Banach space, you have now the operator space pre-dual, means you have to also look at n cross n matrices. The norm is also on the n cross n matrices over the space. So we will assume that the dual operator algebras have identity of norm 1, and we will reserve the symbol m and n for the dual operator algebra. So the kind of representation that we are interested in this setting is the normal representation. So by normal representation, we mean a completely contractive, unital weak star continuous homomorphism pi from the dual operator algebra M into B of H. So pi is a homomorphism from the algebra into bonded operators on Hilbert space. And this is contracting on the matrices level, and this is a homomorphism. So phi of M1 times M2, the algebra will be preserved. So if you have a normal representation like this, it will make the Hilbert space H into a dual operator module. What do we mean by dual operator module? Well, a dual operator module is just a subspace of weak star closed subspace of bonded operators on Hilbert space, which is closed under this operation. So if you multiply, so if this is a module, if you have a, so if you multiply M with X, it stays inside X. And pi is for the normal representation. Or it's a dual operator space and it has a module structure, and plus that the module structure is weak star continuous. And these objects were first studied by Efroth and Duan in the one-Newman algebra case. So for us, one-Newman algebra and weak star algebra, they are the same thing. So these objects were first studied by Efroth and Duan. So we will look at the special tensor product in this setting. So before that, I'm going to give you a definition of weak star Morita equivalence. So suppose we have a two dual operator algebra M and N. We say that M is a weak star Morita equivalent to N if there exists a pair of dual operator module X and Y, whereas X is a left M module, right N module, and Y is left N, right M, such that we can write the first algebra M as a tensor product of a special tensor product of X with Y, and the other algebra N as a tensor product of Y with X. And this is again a complete isometry, isomorphic, and the weak star topology is also preserved here. Well, so we have four things here. We have two algebra, M and N, and two module, X and Y. X is left M, right N module. Y is left N, right M module. And we call this M and X, Y a weak star Morita context. So we are using a special tensor product here, which is called the module version of Hagraf tensor product. So this is the module version of Hagraf tensor product. And this is the definition of this tensor product. Well, so we have two modules, X and Y, where X is a right M module and Y is left M module. So what do we do? How do we get this tensor product? Well, it's a usual Hagraf tensor product, but we quotient it by terms of weak star closure of terms of this form. So you take a identity tensor of this form and take a weak, span it and take a weak star closure of that and quotient it by the Hagraf tensor product, and that's what this tensor product is. So there is a nice, every tensor product has two constructions, one abstract construction and another is the universal property. So the universal property of this tensor product is anytime if you have a completely contracted map, which is weak star continuous in one variable at a time and another variable at a time, such that the module action, so this is a module action, X is a module, right module over M, and Y is a left module over M. So if the module action can be interchanged, so X, the map which takes X and Y, so you can interchange the module action for these kind of maps. So if you have a linear map anytime on this space, then this map can give you a unique, completely contracted map on this space, which is what my tensor product is. So this map will be weak star continuous. It's continuous in the weak star topology. So now we will define what a weak star, what a weak Picard group of a dual operator algebra is. So if A is a dual operator algebra, then we define the weak Picard group to be, which is denoted by the Picard group of A and with W to denote it's a weak Picard group. So weak Picard group is defined as a collection of all AA bimodules which implement the weak star Morita equivalence of A with itself. So instead of now considering two algebra, we just have one algebra. So we are looking at all the bimodules which establish a weak star Morita equivalence of A with itself. Two such bimodules will be identified if they are completely isometrically isomorphic and weak star homeomorphic via AA bimodule map. So the module structure has to be preserved and there should be weak star homeomorphism, means the weak star topology is also preserved. So the multiplication, so on this group, the multiplication is given by this tensor product. So the multiplication of this weak Picard group is given by the module normal Hagraf tensor product. So anytime if you have two modules, X and Y, which is in a weak Picard group of A, means they are weak star Morita equivalents, you can multiply them and the multiplication is just simply the Hagraf tensor product. Any weak star continuous completely isometric automorphism of A defines a weak star Morita equivalence by module A theta, which is just A with usual left module map, but the right module map is coming from this automorphism. So what I'm trying to say here is, anytime if I have a weak star continuous automorphism from the algebra A to A, so this automorphism defines a module structure on A. So the model structure will be X times M will be basically X times theta of M, where both X and M are elements in A. And this module will be denoted by A theta. So what is A theta? A theta is basically A. If left module action is just coming from the algebra, the multiplication of the algebra, and the right multiplication is coming via this automorphism.
That is the multiplication of two elements of the algebra. What happens if you have a constant? So you have this module structure, you need a constant and two internal multiplication.
Yeah, you assume that it has a constant.
So that is also works for a constant?
Yes.
For a constant?
So this is the space itself. The only thing is that the module action is, the left module action is just the multiplication of A, and the right module action is coming via this automorphism. So this is our result. So the bimodule A theta which I defined is a weak star Morita equivalence bimodule for A with the inverse bimodule A theta inverse. So it turns out that A theta and A theta inverse. It turns out that this is a weak star Morita context. So for every automorphism theta, I can define a weak star Morita equivalence bimodule which establishes a Morita equivalence of A with itself. So A theta and A theta inverse are the elements of Picard group of A, the weak Picard group of A. So such kind of bimodules will be called symmetric if the module action is the same. If the left module action and the right module action coincide, which will happen if you look at the function algebra. So this is our theorem for a weak star closed function algebra A. The weak Picard group is a semi-direct product of automorphism group of A and a subgroup of Picard group which consists of symmetric equivalence bimodules. So every element in the Picard group can be written as x theta, where x has it's a symmetric equivalence bimodule and theta is an automorphism of A. So this is the main result, and using this result we can we have proved that the weak Picard group of H infinity is the conformal maps of the automorphism on disk. But we are still working on little bit details in there, so I didn't prove that. So I think I'll stop here. So this is for some of the references. So I'll stop here. Thank you.